Hello, and welcome to this presentation on plotting nonlinear graphs. We're considering primarily quadratic equations of the form y equals ax squared plus bx plus c, which plot parabolic curves, as shown here, this bucket shape, and shown here in this hat shape. We will also briefly introduce plotting cubic graphs. Cubic equations are of the generic form ax cubed plus bx squared plus cx plus d. It is preferable if you've seen a previous presentation relating to the plotting of linear graphs of the form y equals mx plus c, as this provides an underpinning knowledge for the work we're going to look at in this presentation. Graphs of nonlinear equations. In practice, many equations do not follow the linear line law of y equals mx plus c, and so do not produce a straight line when plotted on an xy graph, which is something we looked at in a previous presentation on plotting linear equations. Such nonlinear equations can include the sine and cosine waveforms, logarithmic and exponential curves, and also quadratic curves. And it's the quadratic curves we're primarily going to focus on in this presentation. A quadratic equation is of the second degree and has the form of y equals to ax squared plus bx plus c. Graphs of quadratic functions. As the graph of a nonlinear function is a curve, then more than 3 points must be plotted to provide the shape. However, generally speaking, we usually plot at least 6 points to define the curve. When plotting a linear line, as in the previous presentation, we only actually need 2 points, but we often plot at least 3 to make sure we have the straight line form. As in the previous presentation, for plotting linear lines, we're going to produce a table of x and y values, and we will choose scales on respective axes that accommodate the range of values used. When the points are plotted on our xy graph, they will be joined with a smooth curve. As stated previously, the general quadratic function, the function of x, is of the form ax squared plus bx plus c and has the characteristic shape known as a parabola. An important part of the curve we're going to plot is centered around the parabola's vertex, which we'll consider in a moment. So graphs of quadratic functions continued. Note that quadratic graph forms are always shaped like parabolas, having either a minimum, shown here, or a maximum value, shown here, depending on whether the coefficient a in the quadratic equation is a positive value or a negative value. Note that the maximum and minimum values occur at the vertex location on the parabolic curve. That's a location where the gradient to the vertex is 0. A parabolic curve has a line of symmetry at the maximum or the minimum point. So quadratic graphs have the equation ax squared plus bx plus c equals to 0, where the a coefficient in the equation does not equal to 0. In other words, there has to be an x squared term in the equation to plot the parabola. Quadratic equations have the form y equals ax squared plus bx plus c, and here's just a few comments about the various parameters. The a coefficient relates to the steepness of the quadratic curve, and as we stated on the previous slide, if a is a positive value, it plots a bucket shape, shown here. And if a is a negative value, it plots a hat shape, shown here. For reference, the ratio b upon a relates to which side of the y-axis the vertex lies. If the b upon a ratio is positive, the vertex is on the left-hand side of the y-axis. So in this case, the b upon a ratio would be positive. And if the b upon a ratio is a negative value, then the vertex is on the right-hand side of the y-axis. In this case, the ratio of b upon a would be negative. Just note in the case as the law of the linear line, the constant c in the equation relates to the intercept of the curve with the y-axis. So in this particular curve here, the intercept would be shown here. And again, purely for reference, if you want to determine the actual x value of the vertex, it can be found from the equation negative b divided by 2a. That's given without proof here. That's the actual location of the vertex along the x-axis. We could also find the vertex by using a process called differentiation. That's something we reviewed in a separate presentation. Not only are we interested in the vertex location, we're often interested in the roots of the equation, and note that the roots of the quadratic equation relate to where the curve crosses the x-axis. So these are the roots here, and also the roots shown here. So exercise 1 here, we're asked to plot a graph of the quadratic equation. Y is equal to 3x squared plus 10x minus 8. We're given limits over which to plot the graph. That's x is equal to -6 through to x is equal to 4. Once plotted, we've got to state the location of the roots of the equation and also its vertex. To do this, we're going to use a tabular approach, which is very similar to the approach we used in the previous presentation related to linear lines. But obviously, in this case, we're plotting a quadratic equation. In the table below, I've broken down the equation into the various steps. I've got the 3x squared row, I've got the 10x row, and I've got the -8 row, constant. And by adding up these three terms, we will find the value of y. I've undertaken the calculations when x is equal to 2. So putting 2 into the equation, x squared would be 4, multiplied by 3 produces 12. Putting 2 into the equation here, 10 multiplied by 2 is 20. And of course the constant -8 remains -8. And then adding up the three terms, 12 add 20, take away 8 is 24. I've also now considered the x value of -5, so now putting -5 into the equation. Just be careful of the negative number here. When you're squaring -5, it becomes +25, and then multiplied by 3 produces 75. Putting -5 in this equation, 10 multiplied by -5 is -50. The constant -8 is the same as before, and adding these three values up becomes 17. So there's 2 points we could plot on the graph already. When x is equal to 2, y is equal to 24, and when x is equal to -5, y is equal to 17. Once you've populated the table, you can then find the range of y values over which you need to plot the equation, and you can plot this on a graph. If you think you can complete the table without further assistance and also plot the graph, I would encourage you to stop the presentation and do that now, but the full work solution is shown on the following slide. The answers are shown at the bottom of the question. Exercise 1 continued. I'm just going to evaluate two coordinates here in detail for you. The x equal to 2 column here is already evaluating, so is the x equal to -5. That's from the previous slide. But I'm going to look at x equal to 3 and x equal to -6. Considering the x equal to 3, putting that into our equation, so 3x squared becomes 3 multiplied by 3 squared, and that's equal to 27. Taking the next row, the 10 multiplied by x, that will be 10 multiplied by 3, so that's 30. Of course, the constant -8 remains -8, is not affected by the value of x. And we simply now summate the columns. So 27 add 30 is 57, subtract 8 becomes 49. Let's consider the value of x equals -6. So putting -6 into our equation, that's 3 multiplied by -6 all squared. And be careful here, -6 squared is +36, and multiplied by 3 is +108. In our second row, we have 10 multiplied by -6, and that will equal to -60. And the constant -8 as before remains -8. Adding the three terms together, that gives a y value of 40. Hopefully you've been able to work out the other values of y given values of x. For exercise 1 full solution, so here are the coordinates ranging from x is equal to -6 through to 4 and the associated values of y. We basically plot the y values against the x values on our graph. We do not need to plot individual steps. Exercise 1 continued. Here's a plot of the quadratic equation y is equal to 3x squared plus 10x minus 8. We're asked in the question to find the roots and the vertex. The roots will be where the curve crosses the x-axis. So we can clearly see a root is at -4 here. So x is -4, root occurs. Not quite so easy to see where the root is here, but looking at the scale, it's around about x equal to 0.6 or x is 0.66. And the location of the vertex will be somewhere down here. And that would appear to be around about -1.7 on the x-axis and -16.2 on the y-axis. But therein lies one of the problems with graphical techniques. We're not absolutely sure what those values actually are, but they look in that kind of range. So the vertex in this problem is a minimum. In other words, we're plotting the bucket shape here, and the minimum is the lowest point on the curve. Here are some questions related to graphs of nonlinear equations, quadratic graphs in this case, where we're plotting the lines from the given equation. So questions 1 through to questions 4 are shown on the slide. In question 1, we're asked to plot the equation y is equal to 2x squared minus 7x minus 5 between the range of x is equal to -4 and x is equal to +5. Once we plotted the graph, we have to state the location of the roots and also the vertex, the turning point. I've suggested use the format shown in the table. Here we have x in the first row and then the y values calculated in the second row. The answers to the question are shown in the square brackets on the right hand side. I encourage you to attempt questions 1 to 4. The process is very similar to that shown in the previous example, and all the answers are shown in the brackets on the right hand side. The full work solutions are shown on the following slides. So question 1 is the solution for the equation y is equal to 2x squared minus 7x minus 5 plotted between x is equal to -4 and x is equal to +5. So in my table here, I've got my x values in the top row and my y values in the bottom row, and I've just shown the intermediate steps in between. You didn't need to show them in this case. I've just shown them for completeness. All you need to show is the initial x values and the calculated y values. You can then plot the y against x on the graph. The next slide shows you very detailed calculations of how the y values were obtained from the x values if you're having problems obtaining some of the values shown in the table. Question 1 continued. Here's a more detailed breakdown of the calculations for evaluating the coordinates for the equation y is equal to 2x squared minus 7x minus 5. On the left hand side we're given values of x that we plug into the equation to work out values of y on the right hand side. If you are having problems with the calculations, just be careful of directed numbers. For example, here -3 when it's squared becomes +9, and 2 times 9 would be 18 for this part of the equation. Likewise here we've got -7 multiplied by -3, that will become +21. Just be careful you're not making mistakes with the directed numbers. Another interesting point to note here is when we're putting the values of x into our equations, notice the values of y here have changed their sign, gone from +4 to a -5. So that means a root occurs between, in this case, x is equal to 0 and x is equal to -1, as shown here. Likewise, another root occurs here between x is equal to 4 and x is equal to 5. Those are the x values, because again, we've got a change in sign of the y values. The change of sign of the y value is just a point of reference to note there when you're trying to find roots. In later work we'll be solving equations numerically, and we often want to know roughly what the range of x is where the root occurs. And one way of finding the range of x values is to look for the change of sign of the y values. If you have a change of sign of y, you know a root has occurred between the two x values used. Question 1 continued. Here's the curve plotted from the equation y is equal to 2x squared minus 7x minus 5. Reviewing the graph, we can see that there are roots that occur here at the value of 4 on the x-axis, so x is equal to 4. A root occurs somewhere in this region here, which seems to be around x is equal to negative 0.66. The vertex, which is the minimum in this case, the bottom of the curve in other words, seems to occur somewhere in this region, and that reads roughly 1.75 on the x and negative 11 on the y. Again, that's an estimate by inspection of the graph. And of course this is a minimum. Here's question 3 solution. We're asked to solve the nonlinear function y is equal to 6x squared minus 11x minus 35. We're given a range of x equal to negative 3 to x equal to positive 5. And the range of x values used in our table. Again, I've shown you a complete breakdown here, but you only really need to work out the values of y, and there's the y values in the bottom row. Question 3 continued. Here's a plot of the equation y is equal to 6x squared minus 11x minus 35. From the plot we can see a root occurs here where the curve crosses the x-axis at x is equal to 3.5. And a second root occurs here where the curve crosses the x-axis at around about x equal to negative 1.67. Our vertex appears to occur in this region here, it's a minimum in this case at the bottom of the curve, and that reads it x is equal to 0.9 and y is equal to negative 40. And of course it's a minimum. Question 4. We're asked to plot the nonlinear curve y is equal to 1 plus 3x minus x squared. This is actually a negative a value in this case. It's negative 1x squared. So it will change the shape of the curve. The range we're plotting is x is equal to negative 2 to x is equal to positive 3. Again, in my tabular form, my x values stated here, negative 2 to 3 in increments of 1. And my associated y values are shown in the bottom row. Question 4 continued. Here's a plot of the equation y is equal to 1 plus 3x minus x squared. We can see this time it's a hat shape. Looking at the roots, a root occurs here when x is equal to 3.3. Second root occurs in this region when x looks to be around negative 0.3. And the vertex appears to be here. It's a maximum in this case, it's the top of the curve, and that's at the region of x is 1.5, and reading on the y value, that's in the region of 3.2. And of course that's a maximum this time. Exercise 2, we're going to plot a cubic curve. Very similar approach to the plotting of a quadratic curve. It's just that we've got a power of 3 here. The order is 3. So the equation given is y is equal to x cubed minus 5x squared plus 2x plus 8. And that's between x is equal to negative 2 and x is equal to positive 6. We've got to determine the location of respective turning points in the solution. Again, I've chosen to use a tabular approach here to try and indicate how we break the equation down. You don't need to if you don't want to. You can just simply write the x values in one row and then calculate the y values. But I'm going to show you the very detailed calculations here to show how the equation is broken down. I've evaluated when x is equal to 5 and x is equal to negative 1. So when x was equal to 5, putting 5 into the equation, that would be 5 cubed. 5 times 5 times 5 is 125. Putting x into the next term, the negative 5x squared, that would be 5 squared is 25 multiplied by negative 5, that would be negative 125. Putting x into the next term, that will be 2 multiplied by x, that's 2 multiplied by 5, so that's 10 in this case. Constants as always, the positive 8 constant remains as positive 8. Summating the terms in the column, that becomes 18. So when x is equal to 5, the y is equal to 18. If we consider when x is equal to negative 1, then put in negative 1 for x in the equation. Be very careful there, that's negative 1 cubed, and on your calculators that would be negative 1. In other words, negative 1 multiplied by negative 1 is positive 1, but then multiply it by negative 1 again, it reverts to negative 1. So be careful there. And the value of x into the second part of our equation, that becomes negative 1 squared is positive 1 multiplied by negative 5. That becomes negative 5. Putting negative 1 into the third term, 2 multiplied by negative 1 is negative 2. And the positive 8 constant remains as positive 8. Summating the columns there, we get a y value of 0. So when x is equal to negative 1, we would plot y is equal to 0. I would encourage you to stop the presentation and complete the rest of the table and find the y values. You then need to plot the y against x values on a graph between the range of negative 2 and positive 6 on the x. Find where the maximum turning point location occurs, that's given here in the brackets, and where the minimum turning point location occurs, that's given here in the brackets. The full work solution is shown on the following slide. Exercise 2 solution. We're asked to plot the equation y is equal to x cubed minus 5x squared plus 2x plus 8 between the range of x equals negative 2 and x is equal to positive 6. The table below shows the values of x ranging from negative 2 to positive 6 and then the calculated values of y for the range. The cubic equation is plotted on the following slide. Exercise 2 continued. Here's a plot of the cubic equation y is equal to x cubed minus 5x squared plus 2x plus 8. The question wants us to find the turning points, but I've also highlighted the roots here. There are 3 roots for the cubic equation. We can clearly see a root occurs here when x is equal to 4. A root occurs here when x is equal to 2. And a root occurs here when x is equal to negative 1. So our 3 roots for our cubic equation. For us to find the turning points, we can see we have a maximum turning point, that's the top of the curve here, in the region of 0.2 on the x-axis and about 8.2 on the y-axis. There's the maximum turning points in the x and y coordinates. And we have a minimum in the cubic equation here in the region of x is equal to 3 and the y is equal to negative 4. It's actually stated here as a minimum at x is equal to 3.12 and y is equal to negative 4.06. Those would be the exact answers from an analytical method. But from a graphical method, it's about 3 and negative 4. This illustrates quite clearly one of the problems with graphical solutions is knowing the accuracy of the roots themselves. The analytical solutions obviously are more accurate. Question 5, we're asked to plot the cubic curve of the form y is equal to 3x cubed minus 5 between the range of x equal to plus or minus 2. We've got to find the root and the turning point location. The question suggests use the tabular format shown on the right hand side here. So our x values range from negative 2 to positive 2 using increments of 1 here. And we've got to work out the associated y values. The answers are shown in the brackets for the root and the vertex location. I'd encourage you to start the presentation and attempt question 5, although the full work solution is shown on the following slide. Question 5, we have to plot the cubic equation y is equal to 3x cubed minus 5 over the range of x is equal to negative 2 to x equal to positive 2. In the table below I have shown the range of x values between negative 2 and positive 4, but actually negative 2 to positive 2 was all that is required. The last line shows the y coordinates over the range required. On the following slide I've plotted the curve. Question 5 continued. Here's a plot of the equation y is equal to 3x cubed minus 5. Notice because I've used a range of x between -2 and +4, which is not what the question stated, I've made the graph quite difficult to interpret, to find the root and the turning point. And that's because the location of the turning point appears to be in this region here, and the root appears to be somewhere in this region here. So it's obviously preferable if I plotted between the -2 and +2, it would have made the curve easier to interpret. So just a point of reference, where ranges of x are given in the question, they should be adhered to. On the following slide, you'll see I've tried to enlarge this region here. Question 5 continued. This is the enlarged region from the previous slide. This is our x-axis in this case, and our y-axis. This location here is actually the root, that's where the cubic equations cross in the x-axis, and that looks to be in the region of x is equal to 1.1. And this location here on the cubic equation is actually the turning point. This is where the zero slope is occurring in this particular case. It's actually turning point of contraflector, to use its grand name here. And the turning point appears to be when x is equal to 0 and y is in the region of -5. Notice this value here reads -20 on the y-axis. And finally, some practical applications of solving nonlinear equations. These are quadratics here. Questions 1p through to 4p are contextualized questions that we have actually covered in a previous presentation on solution of quadratics using an analytical method such as factorization or the quadratic formula. But in this case, we're going to solve them using graphical techniques. So these questions are more difficult because they're contextualized. So the first thing to do is to digest the question, extract the information from the question, draw appropriate diagrams, apply appropriate theory to help solve the problem. For example, in question 1, we'll be using Pythagoras' theorem. In question 2, we need to rearrange the equation. Question 3, we'll be using an area formula. And then generate the, in this case, quadratic equation that we're going to solve using graphical methods. If you have already seen the presentation which solves these problems using analytical methods, then you will understand the procedures involved. The main focus here is to actually solve the problem using a graphical technique. If you think you can attempt any of these questions, I would encourage you to stop the presentation and try and attempt the questions, but the full root solutions to questions 1p and 2p are shown on the following slide. Note that the answers are shown in the brackets on the right hand side, and the full root solutions to questions 1p and 2p are shown on the following slides. Question 1p, solution here. A rectangle has sides in the ratio of 3:1 and a diagonal of 16 millimeters in this case. We've got to find the lengths of each side. As I said previously, this is a Pythagoras theorem problem that needs to be applied. So this is essentially the right angled triangle we're considering in this particular question, and Pythagoras theorem applies to right angled triangles only. So applying Pythagoras theorem, square of the hypotenuse, so 16 squared, is equal to the sum of the squares of the other two sides. So 3x squared is this side squared, added to x squared is this side squared. I will let you review the solution at your own pace, but the solution is reviewed on a previous presentation related to solving quadratic equations using analytical methods. The part I'm interested here is taking the equation that we formed in the previous presentation, but this time solving it graphically, not analytically. So what we will do in this case is plot the equation y is equal to 10x squared minus 256 between a range of x, and I've chose -6 to +6, and that's my estimate of the range required in this particular case by trial and error, and I've evaluated the appropriate y values given the x values. On the following slide, I'm going to plot this equation, and then I'm going to read off the values for the roots. Question 1p continued. Here's a plot of y is equal to 10x squared minus 256. And we see it's a quadratic shape here. We're trying to find the roots. Locating the roots in this particular case, we can see one root is at +5, so x is equal to +5 is one root. And we can see another root occurs at x is equal to -5, so our second root x is equal to -5, although in this case that's not a practical root to use. So although x equal -5 is a valid solution for the equation, it's not a valid solution from the practical context of the question. So only x equal to 5 is a valid solution here. Looking at the location of the vertex is a minimum in this particular case. It occurs at x is equal to 0 up here, and the y is equal to -256. That's a minimum. To refer back to the application of Pythagoras' theorem and the sketch of the question, we now know that the x is equal to 5, so b would equal to 5 in this case, and that would make the L is equal to 15. 3 times 5 is 15. The actual answers are 5.06 and 15.18, but from a graphical method, 5 and 15 would be adequate. In question 2p, we're asked to find the value of h given the equation w is equal to 2 multiplied by the square root of, and in brackets, d multiplied by h minus h squared. We're given the value of w is equal to 4. We're given the value of d is equal to 5. So given the equation in the question, we have to transpose the equation to form a quadratic in terms of h. And I'll let you review the algebraic manipulation at your own pace. We did cover this in detail on the previous presentation of analytical methods. The equation you determine is h squared minus 5h plus 4 is equal to 0. Again, that's in the form of a quadratic, but this time in terms of h. We're going to solve the equation using a graphical method, so for values of h, I need to find values of y. I've used a range of h here from 0 to 5 in this particular case. Again, a trial and error approach to try and find the suitable range here, but knowing the ranges of h, I can find the range of y. We'll plot the curve on the following slide. Question 2p continued. Here's our equation, y is equal to h squared minus 5h plus 4, and we can see it's plotted here again as a bucket shape. So the roots occur where the curve crosses the h-axis, in this case the x-axis. So when h is equal to 1, we have a root, and when h is equal to 4, we have a root. We want the location of the vertex, which occurs here. That would be in the region of h is equal to 2.5 and y is equal to -2.25, and that's obviously a minimum. We can now check the solutions by putting the value of h back into the original equation generated and seeing if the answer is going to be 0. You'll find when you put the value of 4 for h into the equation and the value of 1 into the equation, you will get 0. So we have our solutions. For your reference, here's the bibliography used to help generate this presentation. I hope this has been of interest to you, and thank you for viewing.